as my hyperparameter. So coming back to what is the single neuron is doing. So let's say if we have x1 and x2 space, right? Depending on the weights, we are basically finding some sort of a boundary that has a negative half space and a positive half space, and we are elevating one side of the boundary and we are depressing the other side of boundary if our nonlinear squashing function is a sigmoid function. Okay. Another closely related function is a tan H function. Let's look at that carefully. Now the other thing is that we need a smoother transition between the two, because we will be doing gradient descent, and we don't like zero gradients. We like at least some finite gradient, so that we have a direction on about where to move. So these are some popular activation functions. So you are already familiar with this step function, which is not very useful, right? And then we have the sigmoid, which is an approximation, smooth approximation of the step function. The derivative is never truly zero, so we have a direction, we get some direction on how to adjust the weights. So we like using sigmoid function. A very similar function is a tan H function, which instead of going from 0 to 1 will go from -1 to +1 on the left asymptote and the right asymptote. Another very useful function is the rectified linear function. So this is the rectified linear function. So it's 0 on the negative side and its identity on the positive side. And although we have zero derivative here on the negative side, we are not too worried about it, is because we assume that for at least half the number of input samples, the output computed will be on the right hand side and we will get some derivative. There are some advantages of using the ReLU activation function, is that it is easier to train than sigmoid, because on one side the derivative never becomes very, very small, although even in sigmoid theoretically the derivative is never zero, but it becomes very, very small when we go towards an extreme away from the origin. So here, at least for half the inputs, for ReLU the derivative will always be finite, and it has been practically seen that neural networks with the ReLU activation function converge faster, and they give slightly higher accuracy in many practical cases. So basically what ReLU is doing with a single hidden layer, if you have any function, it's trying to map it with some combinations of ReLUs. So you shift these ReLUs left and right, or you flip them around by turning the weights negative, or you increase their slope by increasing the mod of the weights and so forth. But you take many of these and you add them up in the second layer and with different weights, and then what we get is some sort of a piecewise linear approximation of the function that we are trying to model. So it's basically doing this piecewise linear approximation of the function. Another quite useful activation is to do no activation, which is linear, which is identity, and that is what is used in the final layer or in the second layer of a regression neural network, because we want to be able to model so let's say if your y is equal to fx and this y is not a probability. If it was a probability, then it's going to be between 0 and 1, and for that the final layered activation is usually sigmoid, or a generalization of that, which is softmax. But for regression tasks, sometimes we want y to have a large range from -infinity to +infinity. So in that case, the last layer will have no activation, or what is called linear activation. So for a regression net, we will have linear activation. For classification nets, we will have softmax and sigmoids. Sigmoid for binary classification, softmax for n-ary classification. It's a generalization over sigmoid. But for the hidden layers, we can either have tan H, or we can have sigmoid, or we can have ReLU. The preferred one is ReLU, rectified linear unit. So these are the equations for all of these. The step function is just a theoretical construct. We don't use it. It's sine of x plus 1 by half. right? And then you have sigmoid, which is the logistic regression type of a function. Then we have tan h, which is simply tan h, which basically acts as sigmoid stretched 2 times and then shifted down by 1. And then we have ReLU, which is just max of 0 and x, right? And then we have softmax, which if you take I is equal to 2, it takes the form very similar to sigmoid. It's basically just a 2-dimension or 3-dimension or n-dimension generalization over sigmoid. In sigmoid, it is assumed that the output of one classes is 1, for the other class it is e to the power x, whereas here we are computing it for all different classes. If we have more than 2 classes, then we don't take one class as a relative class, we just take all of them. And then we have linear activation, which is just simply identity function. It does nothing to the output. Notice that this is only for the output layer of a regression neural network. It is not to be used in the hidden layers. In the hidden layers, you want to use any of these functions, okay? And the preferred one to be used is ReLU. And there are situations where you don't use ReLU, but those we will leave that for deeper neural networks, for deep learning, when we get to that. So we have already seen what is a sigmoid. It's a smooth transition of the step function, and although I mentioned that ReLU is to be used for hidden units, we have to keep it in mind that it usually does not give us a meaningful output. It gives us a meaningful division of the input space, but it does not give us a meaningful output. So it is usually not used for the output of a neural network, unless you have a very specific reason that you want to restrict, you want to squash all the negative outputs to just 0. And tan h is similar to sigmoid, and it is used for modeling outputs between -1 and +1, usually -1 being negative and +1 being positive, and the intermediate range is to allow for the transition and gradient descent. Softmax is used for n-ary classification. Linear is used for the final layer of the regression. Okay. So now what we can do with these neural networks, we can take inputs, and we need not have a single hidden layer. We can actually add multiple hidden layers before we get to the output. Okay. So such a neural network has, let's say, 2 hidden layers and a final output layer. So this has it has 3 sets of weights. You have a set of weights here, you have a set of weights here, and you have a set of weights here. So you have 3 weight matrices in this particular neural network, and you can keep increasing. We can have actually more than 2 layers also. For now, we will just study a single hidden layer. The problem what happens when you increase the number of layers is that you get too many parameters, and you get something called gradient dilution that we will study a little later. So, but the basic structure of the neural network is the following: that you will have a set of inputs. Inputs will be passed on to the next layer. They will not come back. They will not pass information to each other. They will just pass information to the next layer. That next layer will pass information to the next layer, and that will pass information to the final layer that will compute the output. Okay. So within this, you have a bunch of hyperparameters. So for example, how many layers, how many hidden layers do you need? Okay. So the obvious answer to this is that you need at least 1 hidden layer to model anything nonlinear. Okay, so you need at least 1 hidden layer. And then what is the dimension of the input layer? How many neurons in the input layer? That is easy. That is just that you will have as many the dimension will be same as the dimension of the input. What is the dimension of the output layer? That is also easy. That it is the same as the number of outputs. So if you have 3 classes, then you will have 3 outputs. If you have three-dimensional regression, then you will have 3 outputs and so forth. So the input and the output dimension is fixed. The number of hidden layers is something that you have control over, and that's your hyperparameter. Then within each hidden layer, the number of neurons or the dimension of that layer, the dimension of a hidden layer, is also a hyperparameter. Okay, and then what we have is we have a feed forward structure where information only goes from one layer to the next layer. It's not exchanged within the layer, it doesn't come back to the layer, it doesn't skip layers. Okay, no skipping, no lateral connections, all right, no backward connections. Everything is one layer forward. That's why it's a layered structure. Okay, that's why it has that functional form where one function is nested inside another function, is nested inside another function, is nested inside another function. Okay, so your output layer will represent the output of the neural network. So if you have a 2-class output, you will need only one layer, one output neuron. Sometimes you need more than one. If you have more than one outputs, okay, your input layer represents the number of inputs that you have in your data. Okay, and then you will have just one such layer, and then the number of hidden layers is where you play with the structure of the neural network. You can increase the number of hidden layers, you can increase the number of neurons in each layer, and so forth. So how do we train this? How do we train this neural network? So essentially we train it using gradient descent. Is what we had seen about gradient descent. I will just quickly recap. So let's say you have a function and I want to find the maximum of that function. So you can see that here the slope of the function is positive, so the maximum lies to the right side. Here the slope of the function is negative, so the maximum lies to the left hand side. So at a particular function, if I don't know the form of the function, but I can compute its point value and its point derivative, then I know I need to go right to reach the maximum. Okay, so I will take a small step to the right and then recompute the function and its derivative. If the derivative is still positive, I will keep going to the right. Here, if the derivative is negative, I will keep going to the negative right side, which is the left side, and I will keep going until my gradient is 0. Then I have reached the top of the mountain. And in gradient descent, we take a step towards the negative side of the gradient. So if we have a loss function and we want to minimize it, we will compute its derivative, right? And we will take a function and a step towards the negative side of the derivative. So here at this point, if the derivative is positive, then I will go left. Here, if the derivative is negative, then I will go right until I reach this point. So that is gradient descent. And the derivative of so these derivatives can be computed for vector functions also. For now, we were looking at only scalar functions. In scalar functions means that your output is only one dimensional, f of x is only one dimensional. So let's take the example when you have f of x is equal to ax square plus bx plus c. Your derivative is 2ax plus b and your double derivative is 2a. So what these tell us is that if this blue curve is the function f of x, then my derivative is going to be this red line, and my second derivative is going to be this horizontal green line that you see here, right? For the convex parabola, here we have a concave parabola and everything reverses its sign. So if I want to find the minima or the maxima, then basically I will equate the derivative to 0, which is where this red line is crossing the x-axis. So you can see from the red line basically whether you need to take a step in the right direction or in the left direction for gradient descent or gradient ascent. Okay. Now when we go to multiple dimensions, so let's say we have x1 and x2, then we will not have just parabolas, we'll have bowls or paraboloids. And here we are looking at derivative in two different directions, which becomes the gradient vector, and then we can take a step based on the gradient vector. So if I draw the contours of this parabola, it may look like this, and at any particular point in this particular loss function surface, I will compute the derivative, and that derivative basically will point me in the direction of largest increase. And to do a gradient descent, I will have to take a step in the negative of that direction, a small step in the negative direction. I will reach here, then another small step, etc., etc., and after some iterations I might reach the bottom of this bowl. Okay, so here's an example of a gradient. So here we have two different inputs, x1 and x2, it's a function of two different variables. So in the x1 x2 space, in neural networks it's going to be w1 and w2, not x1 and x2. x1 and x2 are the training inputs, those are going to be fixed. But here, just for the function, we have x1 and x2. We can take the derivative and we will get these two, we will get a vector like this, and we can compute it for a particular point. And this direction, so this direction is basically the unit vector. I computed the derivative at point x1 is equal to 2 and x2 is equal to 1. I got 20 and 6. If I convert it into a unit vector, then I will get a unit direction, and that direction tells me where will I step for maximum increase. If I want to go to the bottom of this, I will go in the negative of this direction. Okay, so this story that is folding in multiple dimensions is that we have, at any particular point, we will go in the negative direction, and then we will reach a new contour, then another negative direction will reach a new contour, and so forth, and ultimately we will reach the bottom. If we take too large of a step, then we will basically be doing some bouncing around. So let me take a different color. For large steps, if our eta is large, then we will be bouncing around until we reach the bottom. And if eta is too large, then we might actually go so far out that we will go outside this contour and we will actually diverge. We will increase the loss value or the function value, and that is also not desirable. Right? So all these concepts are applicable to neural networks as well, and we try to make that computation more efficient using something called the backpropagation algorithm. So we will take this in the next segment of this module, where we will go into backpropagation algorithm and see how it is applied to neural networks. Thank you.